Today we are talking about how to use the difference quotient to turn the derivative into a function, which is denoted here as f prime of x. And this on the right-hand side is the difference quotient. You'll notice that a has been replaced in this context with x because we are finding the derivative at any value. Let's take an example. F of x equals x cubed minus 2x squared. If we want to find f prime of x, we're going to insert these function values. So it turns out to be f prime of x equals f of x plus h. So that's x plus h cubed minus 2 times x plus h squared minus f of x, and that's just x cubed minus 2x squared, all over h. And we can't forget to take the limit as h approaches 0. That's an integral part of our definition for the difference quotient. This then gets expanded to f prime of x equals x plus h cubed minus 2 times x plus h squared, and then minus the quantity x cubed minus 2x squared, which is just minus x cubed plus 2x squared. And this is, again, all over h. And we can't forget to take the limit as h approaches 0, because this actually isn't defined when h is 0. You'll notice here that we can cancel some terms. This 2x squared cancels with this minus 2x squared, and this negative x cubed cancels with this positive x cubed at the front. At this point, we can rewrite the expression to take out an h. So we get f prime of x equals the limit as h approaches 0 of h times 3x squared plus 3x plus h squared minus 4x minus 2h, all over h. These two h's cancel, and we can directly substitute 0 into our equation. And this will then equal 3x squared plus 3x minus 4. Actually, I forgot to put an h here, so there isn't a minus 3x. It's just 3x squared minus 4x. And this is our general derivative. So if we plug in a point, let's say at x equals 1, f prime of x equals 3 times 1 squared minus 4 times 1, and this is negative 1. We know that this is the slope of the tangent line. The slope of the tangent line when x equals 1 is negative 1. You'll also notice that, let's say we wanted to know where the horizontal tangent lines are. We would say 0 equals 3x squared minus 4x. This factors is x, 3x minus 4. So we know that there are zeros for this equation at 0 and 4/3. At these 2 points, we then know that we have horizontal tangent lines on the graph. So it looks something like this. And these horizontal tangent lines means that there's either a relative minima or a relative maxima. So what I drew in the diagram, that's a relative maxima, and this would be a relative minima. So I'll draw arrows to those two. The second example that I'm going to do is f of x equals the square root of 2x plus 3. And before I start, I'm going to ask myself the question, what is the domain of this function? Well, so that you get a real number answer as your output, you need to restrict the domain to have x greater than or equal to negative 3/2. Plug in negative 3/2, you get 0. Anything that's greater than, you get a positive number under the square root, which means there's a real number output. Now I'm going to write the f prime of x notation. So the derivative as a function equals the limit as h approaches 0 of the square root of 2 times x plus h plus 3. So that's f of x plus h minus the square root of 2x plus 3. And this is all over h. The next step here is to multiply both top and bottom by the conjugate. So this is the final equation. The difference between the conjugate and what we had in the numerator was that the sign has changed. And this allows us to multiply them quite nicely. The numerator works out well afterwards. We get f prime of x equals 2 times x plus h plus 3 minus 2x plus 3 in parentheses over h times the conjugate from before. So the square root of 2 times x plus h plus 3 plus the square root of 2x plus 3. The numerator simplifies, and this is obviously the limit as h approaches 0. The numerator simplifies down to h. So we have a negative 2x, a positive 2x, 2h, positive 3, minus 3. So we're left with 2h all over h times, so that conjugate again. The two h's cancel with one another, and you're left with 2 over the conjugate. Now you can directly substitute in h is 0, and you get 2 over 2 square root 2x plus 3. These 2's can cancel, you can simplify this, and you're left with 1 over the square root of 2x plus 3 as your f prime of x. Now I'm going to ask the same question. What is the domain of this new function that is the derivative? Well, the domain is x strictly greater than negative 3/2, because if this turns out to be 0, you have division by 0, which is not permitted in mathematics. So this has to be, you have to restrict the domain to be strictly greater than instead of greater than or equal to, as you are here. The lesson is that the function may not be differentiable on all of the points or on the whole interval where it is defined. Where it is differentiable and where it is defined can be two different places, values, intervals, etc. The third example that I'm going to do is f of x equals 2 minus 2x over 3 plus x. I'm going to ask myself the same question. What is the domain? As I asked this question for the previous example. What is the domain? And it's all numbers, all real numbers, except when x equals negative 3. I'm going to set up my difference quotient, so f prime of x, this is using the derivative as a function, equals the limit as h approaches 0 of f of x plus h. So 2 minus 2 times x plus h over 3 plus x plus h. this is what I'm adding, minus 2 minus 2x over 3 plus x, and this whole quantity is over h. Then I try to combine these by creating a least common denominator, and my least common denominator here is 3 plus x plus h, and that in parentheses times 3 plus x. So in order to accomplish this, for the first fraction, I need to multiply it by both top and bottom by 3 plus x. So I have 2 minus 2x minus 2h times 3 plus x over 3 plus x plus h times 3 plus x. And for the other fraction, I need to multiply by a 3 plus x plus h. So I have 2 minus 2x times 3 plus x plus h over 3 plus x times 3 plus x plus h. So now I have this least common denominator. This is again all over h, and so I can combine the two. And this results in the limit as h approaches 0 of, and I'll multiply this out now, I have 6 minus 6x minus 6h plus 2x minus 4x minus 2x squared, minus 2hx minus, and then I'll put this in parentheses, 6 minus 6x plus 2x minus 2x squared, and then minus 2xh plus 2h. And this is all over h times 3 plus x plus h times 3 plus x. That was our least common denominator from before. And what you'll notice is that this minus 6 cancels with this plus 6, this plus 6, so minus minus, double negative, that's a positive. That cancels with this minus 6x. There is a minus 2h here and a minus 6h. That'll become a minus 8h. This 2x cancels with this minus 2x. This minus 2x, or minus minus, so a positive 2x squared, cancels with this minus 2x squared. This minus 2hx cancels with this, so yeah, this one was positive, minus minus positive, cancels with this minus 2x squared. This minus 2hx cancels with this minus minus 2hx, so this positive. And all that we're really left with is the minus 8h. So I'll rewrite the expression now. This equals the limit as h approaches 0 of negative 8h over h times 3 plus x times 3 plus x plus h. And I can cancel the two h's and then directly substitute in the 0 to get negative 8 over 3 plus x squared. What's the domain? The domain, again, is all real numbers except when x equals negative 3. So in this case, the domain of the differential function is the same as the parent function.